Today we're going to continue reading An Introduction to Analysis by Gunning, and today we're continue with our preparation for the determinant by considering multilinear functions. A linear transformation from a vector space V over field F to the field F itself is called a linear function, or sometimes a linear functional. It's also interesting, of course, to consider linear functions of several variables, or multilinear functions, mappings from v to the k to f from the Cartesian products v to k of a vector space V over the field F to that field F. These are linear transformations in each separate variable, thus the multilinear function v to the k to f associates to any k vectors vi and v a value t of all of those within f, where t of all of these is a linear function of the vector vj when the remaining vector are held fixed. A multilinear function t from vk to f is said to be symmetric if, for any reindexing, t from vj1 up to vjk, and you reassociate j1 with 1, 2, 3 up to k, for any permutation j1 to jk of the indices is said to be, it is symmetric if that is true, and is said to be an alternating multilinear function if we let this is equal to the transformation, or the multilinear functional of vj1 up to vjk is equal to the transformation, or the multilinear map of v1 up to vk, except this up to a sign of j1 up to jk for any permutation of these indices 1 up to k, where this sign term is just the sign of this permutation as we'd find it before. It is convenient to extend the definition by setting the sign equal to 0 if the indices are not a permutation. So for example, if there are any repeated indices. That is, if you ever have two positions being the same, so for instance, if this is v1 and this is v1, the result will be the original thing times 0, since this sign term will be 0 since you have two indices that are the same, namely j1 is associated with 1 and j2 is associated with 1. Both of these, both symmetric and alternating multilinear functions are of considerable interest, but for now, only alternating multilinear functions are what we care about. The following special case is particularly important. This culminates in a theorem, namely that for any field f, there are exactly n, and any n, there's an alternating multilinear function, phi from fn to the fn, fn times fn, like n times, to f, which is a linear functional from the Cartesian product of the n-tuples of f, of n copies of that n-tuple of elements in f. And it is uniquely determined up to a constant factor. This is really preparing us for the idea of a determinant. If phi is an alternating multilinear function, as in 1.67, we'll recall that 1.67 is this phi, which is a linear functional from the set of all n copies of n-tuples to f. Then we can write, and we have a vector vi in f10 written in terms of the basis vectors, as vi is a sum in this way. Then, since phi is multilinear, it follows that phi of all of this is equal to phi of each of these sums, where each of these sums is just each of the v1s up to whatever. And since these are linear in each of these terms, we can pull out each of these sums. Namely, this is the sum of from j1 up to jn equal to 1 up to n of vj1 1 up to vjn n, where we note that the j1 term, or namely the second one on each of the v's, or the second index on each of the v's, is which basis vector, is which element in your list of v1 up to vn you're considering. So for instance, for v1, we have vj11, or I'm sorry, v some index, which we'll call j1 up to n, and then 1. We'll note that all of this is being multiplied by phi on each of the basis vectors, where phi on each of the basis vectors is an element of f. But we'll recall that since phi is assumed to be alternating, then we know that phi of j1 up to jn is simply the sign of j1 up to jn of phi of delta 1 up to delta n. Thus, if there is a multilinear function, we can write it as phi of v1 is equal to c times the sum of each of the sign times each of these terms, where the sign comes from reindexing back down to delta 1. We'll recall that delta 1 is, that C is the phi of a standard basis. That is, we've now shown that any phi that is multilinear is determined up to this constant factor C, which we define to be the phi on the standard basis in its standard orientation, or in its standard listing. That is how, and your definition of standard will change your constant C, but otherwise it is uniquely determined. Conversely, if we have a mapping defined in this way, i.e. that phi of all of these, that phi of v1 up to vn is defined as this entire term, we'll see that it's a alternating multilinear function. Since each term vj11 up to vjn has exactly one factor from each column, and phi of v1 up to vk is equal to c times this sine term times each of these. But we'll note that we can just reorder this sine term into this product, where we can now take it as the sine of k1 up to kn times j1 up to kn, where we now have indices vj1 k1 up to vjn kn. But we'll recall, since we're summing over these, that this is simply a sine of k1 up to 1, kn up to n, times v1 up to vn, where these v1 up to vn's are the vectors, once we take the sum back in and we apply the definition of C. This is shown the second direction, namely that if you have something of this form, which is it's true up to a constant, it is an alternating multilinear function. With that, we have our proof, and we have shown that for any set of n-tuples, there is a unique alternating linear function up to a constant factor, and that linear function is a linear functional in the sense that it goes to f, down to scalars. This is essentially our determinant, because we see we're going to take n vectors, so we can think about this as a square matrix, and takes us n vectors and send them to a number, in the same way the determinant takes any matrix and sends it to a single scalar. With that, we have a lot of our prep work, and we're about to go ahead and define the determinant.